So our next unit is going to look at the concept of momentum. And momentum is commonly thought of how hard it is to stop an object. Now, this is a little bit different than when we talked about inertia, and that inertia was the idea of how hard it was to change an object's motion. And remember, inertia was based on object's mass, okay? Whereas momentum is how hard it is to stop an object. And so what has to be true is that if we have to stop it, that means something has to be moving. And so momentum is not something that it's not something that we physically can measure, but it's something that we can calculate based on other measurements that we have on an object. And momentum is determined by an object's mass and velocity. Now, we label momentum with a P, and it's simply mass times velocity, right? It's a pretty simple calculation for us. The units for momentum are going to be simply the units for mass and velocity. It's going to be kilograms, meters per second. So notice this is different, whereas, acceleration, or excuse me, 1 Newton is a kilogram meter per second squared because it's mass times acceleration. There is no, shorthand for what kilogram meters per second is. It is just kilograms meters per second. It is a vector quantity, meaning that momentum has both a magnitude and a direction, and the direction is the same as its velocity. So if something is moving to the right, that's the direction that its momentum is pointing. And what's true is that momentum is often confused by just how big something is, but it can still also have a large momentum even if it has a small mass and has a large velocity, right? So a large object traveling with a slow speed can have the same momentum as a smaller object traveling with a greater velocity. Those momentums can be the same because obviously we just need to have the product of their mass and velocity be equal. Now, momentum is often related to Newton's second law, where remember Newton's second law was F equals ma. Right? And we said that when the net force on an object is greater than 0, then the object will be accelerating. And so remember, acceleration is a change in velocity. So the rate of change of momentum is equal to the net force applied to it. All right, so remember, a change in velocity. So we can rewrite Newton's second law as F equals m delta v, right? Where this is a change in velocity, okay? And so what we see is a force, let me start over with this. We can rewrite this as force equals mass times change in velocity over time. That's acceleration. Remember, acceleration is change in velocity over time. Excuse me. So what we can say is if we take this, and what we see mass times velocity, right? Mass times change in velocity. Well, that is a change in momentum, right? A change in mom or a change in momentum. And so if we were to rearrange this and get time to the other side, we'd multiply each side by time. And we get force times time equals mass times change in velocity. And that is what brings us to this idea of an impulse, okay? And this is what we call when an object's momentum changes. And this can be because of really 3 things that we can talk about. There can also be other reasons, and we'll talk about that specifically, but an object can speed up, an object can slow down, or an object can change direction. Those would all 3 change an object's momentum. Remember, momentum is a vector, so it has both a magnitude and a direction. So if the direction changes, then there is a change in momentum. And we're going to use this equation here as our equation for an impulse. Right? This portion here, force times time, is typically considered an impulse. Right? When we apply a force for a set period of time, that product of those values is called an impulse, and that's going to result in a change in momentum. Sorry, change in momentum, a change in mom. Right? So force times time equals mass times velocity final minus velocity initial. All right. Two examples of how we would use this. First, it says, estimate the average force on a tennis ball, which has a mass of 0.06 kilograms, that is served at 55 meters per second if it is in contact with a racket for 4 times 10 to the negative 3 seconds. So if we think about this, here's our racket. Right? And a racket is going to hit a tennis ball. Now, we're going to be in contact with that tennis ball for a very short period of time, 4 times 10 to the negative 3 seconds. Right? It wants us to estimate the average force. So force is really what I'm looking for in this case. The mass is 0.06 kilograms. And then we need two velocities, my initial velocity and my final velocity. Well, my initial velocity is 0. Before I hit the ball has a velocity of 0. And after I hit the ball, my velocity final is going to be traveling at 55 meters per second. So if we think about the momentum of the ball, the initial is mass times velocity, which is mass times 0, which is 0. So the ball had 0 momentum. Now the final then would be after the ball is moving, which would be mass times 55. And that would be my final momentum. So if we put this into the idea that, an impulse, a force times the time, equals a change in momentum. Momentum is P. That's how we indicate momentum. So force times time. And guys, again, we're doing this without numbers, because remember, the numbers don't matter. We just need to be able to solve through the problem. A force times the time results in a change in momentum. A change in momentum means we have a mass with a changing velocity. My initial velocity is 0, so we have force times time equals mass times velocity final. And then we can divide each side by t and get that the force on average was the mass times the velocity final divided by my time. I'll let you guys plug those in and get my answer. But that's how I would solve this for my average force based upon what my racket is doing. Now, if we think about this, right, think about what's happening for a ball that's hitting the racket. Let's do one more quick example then. What is the force a car exerts on the water coming out of a hose I don't know what this is, but we can work through it, right? So here's our you know what? Let's just, I haven't looked at this, so let's just stop with that. That will be our examples of momentum, and we'll deal with the rest another time. This is a pretty common idea So here's a great example of how physics and sports go together, right? We have the impulse and momentum of a tennis ball here, right? And when you have a racket that hits a tennis ball, it's not like the ball stays perfectly circle, right? And it's not like the racket stays perfectly in line. The racket is going to stretch back a little bit because the ball is pressing on it, and the ball itself is going to flatten a little bit. So there's also work being done, right? Because the force is applying some distance here, right? Or when we flatten the tennis ball, there is some distance which the force is applied. So not only is there momentum at play here, there's also work and energy, right? But what we see is that as the racket is in contact with the ball for a certain period of time, there's an impulse, and that impulse is going to result in a change in momentum. Now, when we say in our problem earlier that it's the average force, that's really because if we were to look at a graph of the force versus time, we would get a graph that looks a little bit more like this, where we have, right as the racket starts touching the ball, there's a small force. Now, because that racket's strings stretch, right, there is some elasticity, right? Where remember, force equals kx, right? As well as the ball. The ball is elastic. It's going to bounce back to what it was. And so as the ball gets compressed, there is an elastic force, right, of kx in some fashion. And so we have this force that increases the further that these stretches, this axis is. And then as those rebound, that force decreases, right? And so on a force versus time graph, we actually get the area under this curve being the impulse or the change in momentum that's going to occur during this force. So my max force would be up here, right? Whereas my average force, might be here. Okay, so this would be what we're solving for, understanding that the maximum would be actually up here because of the idea that our forces are going to differ based on the stretch of the tennis ball and of the racket.